For tonight's sleep story, we journey back to the very beginning of human understanding, to a time when the first marks were made in sand and the first boundaries were drawn. This is a chronological exploration of geometry, from ancient river valleys to the edges of the cosmos. The story unfolds slowly and gently, designed to guide you peacefully into sleep as we move from simple concepts to more abstract, dreamlike ideas. Let your mind drift along with the narrative, knowing that each section builds naturally on what came before, following the actual historical development of geometric thought across thousands of years. In the beginning, there was only emptiness. No shape, no form, no boundary between one thing and another. The universe existed as pure potential, waiting for the first mark to be made, the first distinction to emerge from the void. Long before numbers had names, before writing existed, before cities rose from the earth, human hands reached out to understand space itself. The story of geometry begins not with theorems or proofs, but with survival, with the need to measure, to divide, to claim a portion of the infinite world and call it home. The Nile River flooded every year, as reliable as the sun's journey across the sky. The ancient Egyptians watched the dark, fertile waters rise and spread across their fields, erasing the careful boundaries they had drawn between one farmer's land and another. When the waters receded, the land was renewed, rich with silt, perfect for growing crops. But the boundaries were gone, dissolved back into the earth. The rope stretchers emerged from this necessity. These were the Harpadanapti, the surveyors of ancient Egypt, who carried with them knotted ropes measured with precise intervals. They walked the moistened earth after each flood, recreating the world that the river had unmade. Their ropes were marked at specific lengths, 12 units forming a sacred tool. They would stretch these ropes into triangles, 3 units on one side, for on another, 5 on the third. The corners always formed perfect right angles, true and reliable, allowing them to rebuild the grid of civilization after nature's annual erasure. This was geometry before it had a name. The word itself would come much later, from the Greek geo meaning earth and metron meaning measure. Earth measurement. The science of space was born from mud and water, from the practical need to restore order after chaos. The Egyptians knew other shapes too. They built monuments that have outlasted empires, structures so precise they still confound modern engineers. The Great Pyramid of Giza, constructed around 2560 BCE, demonstrates an understanding of geometric principles that seems almost impossible for its time. Each side of its square base measures approximately 230 meters, and the variation between the longest and shortest sides is less than 20 centimeters. The sides align almost perfectly with the cardinal directions of north, south, east, and west. The angle of the pyramid slopes, the ratio of its height to the perimeter of its base, the internal chambers and passages, all speak to a sophisticated grasp of spatial relationships. The ancient builders worked with copper tools and wooden sledges, with ropes and human labor, yet achieved accuracies that modern construction would struggle to match. But the Egyptians were practical people. They knew what worked. They knew that certain ratios produced stable structures, that certain angles created spaces that could bear enormous weight. They recorded their methods in papyri, such as the Rhind mathematical papyrus, copied around 1550 BCE from earlier sources. These documents show calculations for areas and volumes, methods for dividing land fairly, techniques for measuring slopes and heights. Yet there was something missing. The Egyptians knew the how of geometry, but they did not ask why. They knew that a rope stretched with sides of 3, 4, and 5 units would create a right angle, but they did not wonder about the deeper truth that connected these numbers. They were content with what worked, with methods proven by generations of use. The shift from practical measurement to abstract thinking, from craft to philosophy, required a different kind of mind. It required people willing to look beyond immediate utility, to seek principles that existed independent of any particular application. This transformation would occur far from the banks of the Nile, on the sun-soaked islands and coastlines of the ancient Greek world. Thales of Miletus walked along the harbor, watching ships arrive from distant ports. It was the 6th century BCE, and Miletus was one of the great cities of Ionia, a place where cultures met and traded, where Egyptian knowledge mingled with Babylonian astronomy, where ideas flowed as freely as goods. Thales was a merchant himself, successful in business, but his mind wandered to questions that had no market value. He gazed at the shadows cast by the masts of ships, by the columns of temples, by his own body standing in the afternoon sun. He noticed that all shadows changed in the same proportion as the day progressed. A tall mast and a short post had shadows that grew and shrank in harmony, maintaining a constant relationship. This observation led him to a remarkable achievement. Thales measured the height of the Great Pyramid of Egypt using only shadows and simple ratios. He placed a stick in the ground and waited for the moment when the length of its shadow equaled the height of the stick. At that precise moment, he reasoned the shadow of the pyramid would also equal its height. He had discovered the principle of similar triangles, the idea that shapes of different sizes could share the same essential form, the same internal relationships. But Thales went further. He did not simply observe that this method worked. He sought to understand why it worked. He wanted to prove that it must always work under all circumstances as a matter of logical necessity. This was a new kind of thinking, a demand for certainty that went beyond mere observation. Thales is credited with several geometric proofs, though the exact details have been lost to time. Ancient sources tell us he proved that a circle is bisected by its diameter, that the angles at the base of an isosceles triangle are equal, that vertical angles formed by intersecting lines are equal. These statements seem obvious now, so fundamental that it requires effort to imagine a time when they needed proving. But obviousness is not the same as proof. Proof requires showing that something must be true, deriving it from simpler truths, building a logical chain that cannot be broken. After Thales came Pythagoras, a figure wrapped in legend and mystery. Born around 570 BCE on the island of Samos, Pythagoras traveled extensively, perhaps to Egypt, perhaps to Babylon, absorbing knowledge from ancient cultures. Around 530 BCE, he established a community in Croton, a Greek city in southern Italy. This was not merely a school but a way of life, a philosophical and religious community bound by strict rules and devoted to the study of mathematics, music, and the nature of reality itself. The Pythagoreans believed that number was the fundamental principle of the universe, that all things were, at their deepest level, numerical relationships. They saw mathematical truth as eternal and perfect, existing in a realm beyond the physical world of change and decay. To study mathematics was to touch the divine, to glimpse the underlying order of existence. The theorem that bears Pythagoras' name represents one of the most important discoveries in human history. For any right-angled triangle, the square of the length of the longest side, the hypotenuse, equals the sum of the squares of the other two sides. If one side measures 3 units and another measures 4 units, then the hypotenuse measures exactly 5 units, because 3 squared is 9, 4 squared is 16, and 9 plus 16 equals 25, which is 5 squared. But this relationship extends far beyond any particular set of numbers. It is a universal truth about space itself, about the very structure of how distances relate to one another. The Pythagorean theorem works for any right triangle with any measurements in any location at any time. It worked before humans existed and will continue to work long after we are gone. The Pythagoreans proved this theorem, demonstrating that it must be true through logical reasoning. While Pythagoras himself left no writings, and the work of his followers was often attributed to him collectively, the proof they developed showed that this relationship emerged necessarily from the properties of space and shape. Yet this beautiful discovery led to a crisis that shook the foundations of Pythagorean philosophy. They believed that all numbers could be expressed as ratios of whole numbers, that the universe was fundamentally rational in this sense. But the Pythagorean theorem revealed something disturbing. Consider a square with sides of length 1 unit. The diagonal of this square, connecting opposite corners, forms the hypotenuse of a right triangle with sides of 1 unit each. According to the Pythagorean theorem, the square of this diagonal equals 1 squared plus 1 squared, which is 2. Therefore, the diagonal has a length equal to the square root of 2. Hippasus of Metapontum, a Pythagorean philosopher, made a shocking discovery around 500 BCE. He proved that the square root of 2 could not be expressed as a ratio of whole numbers. No matter how carefully one searched, no fraction would ever equal exactly the square root of 2. The number was irrational, literally without ratio, existing in a space between all possible fractions, forever inexpressible in the rational terms the Pythagoreans held sacred. Legend says that Hippasus was drowned at sea for revealing this secret, though the truth of this story cannot be verified. What is certain is that this discovery revealed a depth to mathematical reality that had not been anticipated. Geometry had led to numbers that transcended the counting numbers and their ratios, suggesting that space itself was richer and stranger than the simple whole number relationships the Pythagoreans had imagined. Plato stood in the Academy, the school he had founded in Athens around 387 BCE, and looked at the inscription above the entrance, "Let no one ignorant of geometry enter here." For Plato, geometry was not merely a practical skill or an intellectual exercise. It was the bridge between the imperfect world of physical things and the perfect world of eternal forms. In Plato's philosophy, the objects we see around us are mere shadows of perfect ideals that exist in a realm beyond our senses. A circle drawn in sand or scratched on papyrus is never truly circular. It has rough edges, irregular curves, imperfect symmetry. But the ideal circle, the form of circularity itself, is absolutely perfect, with every point on its edge exactly equidistant from its center. This perfect circle cannot be seen or touched, but it can be known through reason, contemplated by the mind. Every physical circle is an approximation, a flawed copy of the perfect form. The compass slips slightly. The hand trembles. The surface is uneven. Yet despite these imperfections, the mind grasps the ideal. Through the imperfect drawings, reason perceives the perfect circle that exists beyond the physical realm, eternal and unchanging. Geometry, for Plato, was the study of these perfect forms. When we prove something about triangles, we are not proving it about any particular physical triangle. We are discovering truths about the eternal, unchanging triangle itself, the perfect form that all physical triangles imperfectly represent. This was a radical departure from the Egyptian and Babylonian approach to geometry. Those ancient civilizations used geometric relationships for practical purposes, measuring fields, constructing buildings, calculating volumes of grain. Plato elevated geometry to the realm of pure thought, making it a pathway to truths that transcended the physical world entirely. Plato believed that studying geometry trained the mind for philosophy. The logical reasoning required to follow geometric proofs, the ability to perceive abstract relationships, the recognition that truth could be demonstrated through pure reason, all prepared the student for deeper philosophical inquiry. The soul, according to Plato, existed in the realm of forms before birth. Learning geometry was actually a process of recollection, of remembering what the soul once knew. Plato was particularly fascinated by certain three-dimensional shapes that seemed to embody geometric perfection. These were the regular solids, three-dimensional figures where every face is the same regular polygon and every vertex is surrounded by the same number of faces. There are exactly 5 such shapes and only 5. The tetrahedron with 4 triangular faces, like a pyramid. The cube with 6 square faces. The octahedron with 8 triangular faces. The dodecahedron with 12 pentagonal faces, and the icosahedron with 20 triangular faces. Why exactly 5? The answer lies in the geometry of vertices. At each vertex, several faces meet. The angles of these faces must sum to less than 360 degrees, or the figure would be flat rather than three-dimensional. With equilateral triangles each having 60-degree angles, 3 can meet at a vertex, forming the tetrahedron. For triangles give 240 degrees, forming the octahedron. 5 triangles give 300 degrees, forming the icosahedron. 6 triangles would create a flat surface. With squares at 90 degrees each, 3 can meet at a vertex, forming the cube. For squares would give 360 degrees, creating flatness. With regular pentagons at 108 degrees, 3 can meet to form the dodecahedron. For pentagons would exceed 360 degrees, making such a configuration impossible. Thus, the 5 Platonic solids emerge as geometric necessities, the complete and exhaustive list of regular three-dimensional forms. These 5 shapes, now called the Platonic solids, seemed to Plato to represent something fundamental about physical reality. In his dialogue Timaeus, written around 360 BCE, he associated 4 of them with the classical elements. The tetrahedron represented fire, its sharp points reflecting fire's piercing quality. The cube represented earth, its stability suggesting the solid nature of ground beneath our feet. The octahedron represented air. The icosahedron represented water, its many faces suggesting fluidity. The dodecahedron was special. Plato associated it with the cosmos itself, with the shape of the universe as a whole. This regular solid, with its 12 pentagonal faces, represented the ultimate container, the space within which all existence played out. Plato's student Aristotle did not share his teacher's mysticism, but he too saw geometry as fundamental to understanding nature. Aristotle studied at the Academy for 20 years before establishing his own school, the Lyceum. His approach was more empirical, more concerned with the physical world as it actually exists, but geometry remained central to his investigations. Aristotle believed that the circle was the most perfect of all shapes, and that circular motion was the natural motion of the heavens. The celestial spheres that carried the planets and stars moved in perfect circles, he argued, because circular motion was eternal and unchanging, without beginning or end, perfectly suited to the eternal and incorruptible nature of the heavens. Aristotle also contributed to the logical structure of geometry. He analyzed the structure of geometric proofs, identifying the roles of definitions, axioms, and theorems. He distinguished between axioms, which were self-evident truths requiring no proof, and theorems, which required demonstration. These logical investigations laid groundwork for the systematic presentation of geometry that would culminate in Euclid's work. While Plato and Aristotle debated the philosophical significance of geometric forms, other Greek mathematicians pursued geometric knowledge for its own sake, building a systematic body of proofs and theorems. Eudoxus of Cnidus, who lived from approximately 408 to 355 BCE, developed the method of exhaustion, a technique for finding areas and volumes by approximating them with simpler shapes. This method would prove essential for later developments in mathematics. The method of exhaustion worked by inscribing and circumscribing polygons within and around a circle. By increasing the number of sides, the polygons approached the curved figure more closely. Eudoxus showed that by this process, one could determine the area or volume to any desired precision without requiring infinite divisibility, using instead a logical argument about limits. But the culmination of Greek geometry came with Euclid of Alexandria, who lived around 300 BCE. Almost nothing is known about Euclid's life. We do not know when he was born or when he died. We know only that he taught in Alexandria, the great center of learning established by Alexander the Great on the Mediterranean coast of Egypt. Euclid's achievement was not primarily in discovering new geometric truths, though he did prove new theorems. His achievement was in organization, in taking the scattered knowledge of centuries and arranging it into a single logical system. This system was recorded in 13 books known as the Elements, perhaps the most influential textbook ever written. The Elements begins with definitions. A point is that which has no part. A line is breadthless length. A surface is that which has length and breadth only. These definitions are austere, stripped of everything unnecessary, pointing to pure ideas beyond physical representation. Then come the common notions, self-evident truths about equality and magnitude. Things equal to the same thing are equal to each other. If equals are added to equals, the wholes are equal. The whole is greater than the part. These statements seem so obvious they hardly need stating, yet they form the bedrock on which everything else will be built. Next come 5 postulates, statements assumed to be true without proof, serving as the starting points from which all else will be derived. A straight line can be drawn between any 2 points. A finite straight line can be extended continuously in a straight line. A circle can be drawn with any center and any radius. All right angles are equal to one another. And the fifth postulate, more complex than the others, concerning parallel lines. If a straight line crossing two other straight lines makes the interior angles on one side less than two right angles, then the two lines, if extended indefinitely, will meet on that side. From these foundations, Euclid built an edifice of geometric knowledge, proof following proof in logical sequence. Each proposition depended only on what had been proven before it. Nothing was assumed, nothing was taken on faith. The system was completely rigorous, completely transparent in its reasoning. Book 1 of the Elements proves fundamental properties of triangles and parallelograms. It culminates with Proposition 47, a proof of the Pythagorean theorem. This proof is different from earlier demonstrations, working directly from Euclid's axioms and previous propositions, showing with absolute certainty that the relationship between the sides of a right triangle is not merely an observed fact but a necessary consequence of the nature of space itself. The later books of the Elements explore progressively more advanced topics. Book 2 deals with geometric algebra, showing how areas can represent numerical relationships. Book 3 investigates circles and their properties. Book 4 shows how to inscribe and circumscribe regular polygons in circles. Books 5 and 6, incorporating the work of Eudoxus, develop the theory of proportion, showing how to compare magnitudes of different kinds. This theory was necessary because of the existence of irrational magnitudes like the square root of 2, which could not be captured by simple numerical ratios. Books 7 through 9 deal with number theory, the properties of whole numbers themselves. Book 10 classifies various types of irrational magnitudes, a technical tour de force that distinguishes numerous subtle cases. Books 11 through 13 extend geometry into 3 dimensions, culminating in the construction of the 5 Platonic solids and a proof that there can be no others. The Elements ends with these perfect forms, these shapes that had captivated Plato's imagination, now proven to be all that is possible, the complete catalog of three-dimensional regularity. The Elements was not the only important geometric work of this period. Apollonius of Perga, who lived from approximately 240 to 190 BCE, wrote a treatise on conic sections, the curves formed by slicing a cone at various angles. These curves, the ellipse, the parabola, and the hyperbola, would prove essential to understanding planetary motion and the paths of projectiles. Archimedes of Syracuse, who lived from approximately 287 to 212 BCE, pushed the boundaries of geometric knowledge even further, calculating the areas and volumes of curved figures with breathtaking ingenuity. But Euclid's Elements remained the foundation, the essential starting point for anyone studying geometry. For more than 2,000 years, it served as the primary textbook of mathematics, translated into Arabic, Latin, and eventually every major language. More copies were printed than any book except the Bible. Students from Baghdad to Beijing studied its proofs, trained their minds on its logical progressions. Islamic scholars preserved and extended the Elements during the European Middle Ages. When the Elements was translated into Latin in the 12th century, it became a cornerstone of European education. In the Renaissance, printed editions made it widely available. Artists studied geometry to perfect perspective. Architects used geometric principles to design buildings. Isaac Newton wrote his Principia Mathematica in geometric style, using propositions and proofs modeled on Euclid. Abraham Lincoln studied the elements to train his mind in logical reasoning. Einstein studied geometry with enthusiasm, later recalling the wonder he felt at geometric theorems. The elements represented something profound about human thought. It showed that starting from a handful of simple assumptions, pure reason could construct an entire universe of knowledge. It demonstrated that certainty was possible, that some truths could be known absolutely, not through observation or authority, but through the inexorable logic of proof. The pentagon is a restless shape. Unlike the triangle or the square, which tile perfectly to fill a plane, pentagons leave gaps, creating tensions and relationships that ripple outward in surprising ways. When the ancient Greeks studied the regular pentagon with its 5 equal sides and 5 equal angles, they discovered something hidden in its geometry, a number that would echo through mathematics and nature for millennia. Draw a regular pentagon. Connect each vertex to the 2 non-adjacent vertices, creating a 5-pointed star inside. The diagonals intersect in a specific way, creating smaller pentagons and triangles within the figure. Measure the length of a side of the pentagon, then measure the length of a diagonal. The ratio between them is always the same, approximately 1.618 to 1. This number appears again and again within the pentagon's geometry. Divide a diagonal by a side, 1.618. Divide a longer segment of an intersected diagonal by the shorter segment, 1.618. The number emerges inevitably from the fivefold symmetry, a mathematical constant arising from pure spatial relationships. The pentagon cannot be drawn without invoking this ratio. It is woven into the very structure of fivefold regularity. The Pythagoreans knew this ratio, recognizing it in the pentagram, the 5-pointed star that served as their secret symbol. The pentagram contained this proportion repeatedly in every intersection, every segment, every relationship between its parts. Though its first systematic study is attributed to Euclid. In Book 6 of the Elements, Proposition 30, Euclid shows how to divide a line segment so that the ratio of the whole line to the larger part equals the ratio of the larger part to the smaller part. This division, later called the golden section or the golden ratio, produces that same number, 1.618. Euclid did not use decimal notation, which had not yet been invented. He did not have a single symbol for this number. He described it in terms of geometric relationships, of lines divided in extreme and mean ratio. But the ratio itself was clear, definite, existing independently of how it might be expressed. The Greeks understood it purely through geometry, through the relationships of lengths and the proportions of figures. The golden ratio possesses remarkable mathematical properties. If you take a golden rectangle, a rectangle whose length and width are in the golden ratio, and remove a square from it, the remaining rectangle is also golden. This process can be repeated infinitely, each step creating a smaller golden rectangle, spiraling inward toward a point. Drawing quarter circles in each successive square creates a spiral that approximates shapes found throughout nature. The self-similarity of the golden rectangle reflects a deeper truth. The ratio reproduces itself through simple geometric operations. Remove a square, and the proportion persists. This recursive property, this ability to maintain its character through transformation, makes the golden ratio unique among all numbers. The number cannot be expressed exactly as a decimal. It goes on forever without repeating. 1.61803398887, but it can be expressed exactly in terms of simpler numbers. The golden ratio equals 1 plus the square root of 5 divided by 2. This formula connects it to the irrational square roots that so troubled the Pythagoreans, yet it emerges from the most basic operations: addition, division, and the square root. The golden ratio has an inverse that is simply the golden ratio minus 1, 0.618. This means that 1 divided by the golden ratio equals the golden ratio minus 1. No other positive number has this property. The golden ratio and its reciprocal differ by exactly 1, a unique mathematical relationship. This creates an algebraic identity. Phi squared equals phi plus 1, where phi represents the golden ratio. In the 3rd century BCE, Euclid proved in Book 13 of the Elements that the ratio of the diagonal of a regular pentagon to its side is the golden ratio. He used this to construct the regular dodecahedron, that Platonic solid with 12 pentagonal faces. The dodecahedron is built entirely from golden ratios, its geometry saturated with this special number. Every measurement within the dodecahedron relates to every other measurement through this single proportion. The construction of the dodecahedron was the culmination of the elements, the final proposition in the final book. Euclid had built his entire geometric system toward this moment, showing how the 5 regular solids could be constructed and proving they were the only possibilities. The dodecahedron, infused with the golden ratio, represented the pinnacle of geometric perfection, the most complex of the Platonic solids. Centuries later, mathematicians studying number sequences discovered the golden ratio emerging from an entirely different direction. Leonardo of Pisa, known as Fibonacci, was born around 1170 CE in the Republic of Pisa. His father was a merchant who worked in Bugia, a Mediterranean port in what is now Algeria. Young Leonardo traveled with his father, learning the arithmetic systems used by Arab and Indian merchants. He observed how Hindu-Arabic numerals made calculation vastly simpler than Roman numerals, enabling merchants to perform complex computations with ease. In 1202, Fibonacci published the Liber Abaci, a book that introduced Hindu-Arabic numerals to European mathematics. The book was revolutionary, demonstrating practical applications of arithmetic to commerce, currency conversion, calculation of profit and interest. Among the many problems in this book was a question about rabbit populations. Suppose a pair of rabbits produces a new pair every month, and each new pair begins reproducing after 1 month. Starting with 1 pair, How many pairs exist after 1 year? The answer produces a sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. Each number is the sum of the two preceding numbers. This sequence, now called the Fibonacci sequence, seems at first to have nothing to do with geometry or the golden ratio. Fibonacci presented it as a recreational problem, a mathematical curiosity about population growth. But examine the ratios between consecutive Fibonacci numbers. 2 divided by 1 equals 2. 3 divided by 2 equals 1.5. 5 divided by 3 equals 1.667. 8 divided by 5 equals 1.6. 13 divided by 8 equals 1.625. As the numbers grow larger, the ratio gets closer and closer to 1.618, approaching the golden ratio with increasing precision. By the time you reach 89 divided by 55, the ratio is 1.6181818, differing from the golden ratio by less than 1 part in 10,000. This connection was not understood in Fibonacci's time. It would not be formally proven until the 18th century, when mathematicians developed the tools to analyze infinite sequences and their limits. But the golden ratio and the Fibonacci sequence are mathematically inseparable, two different manifestations of the same underlying pattern. The Fibonacci sequence provides rational approximations to the irrational golden ratio, each approximation better than the last. The mathematical explanation lies in the recursive nature of both. The Fibonacci sequence is defined recursively. Each term is the sum of the two preceding terms. The golden ratio is defined by its self-replicating property. It equals 1 plus its own reciprocal. These two recursive definitions lead inevitably to the same limiting value. Nature, indifferent to human theorems, generates the golden ratio and Fibonacci numbers through growth processes. The florets in the center of a sunflower arrange themselves in spirals. Count the spirals going clockwise, then count those going counterclockwise. The two numbers are typically consecutive Fibonacci numbers, 34 and 55, or 55 and 89, or in large sunflowers even 89 and 144. This arrangement is not coincidental. As the sunflower grows, new florets form at the center and are pushed outward by later florets. Each new floret forms at a specific angle from the previous one. If this angle were a simple fraction of a full rotation, like 1/2 or 1/3, the florets would align in straight rows, creating inefficient gaps. The golden angle, approximately 137.5 degrees, is the most irrational angle, the one that takes the longest to repeat its pattern. Using this angle produces the most uniform distribution, packing florets as efficiently as possible. The pine cone follows the same pattern. Its scales arrange in spirals, usually 8 spirals in one direction and 13 in the other, or 5 and 8 in smaller cones. The pineapple shows 8 spirals in one direction, 13 in another, and sometimes 21 in a third direction, all Fibonacci numbers. Cauliflower and Romanesco broccoli display spiraling florets in Fibonacci numbers, creating their distinctive fractal appearance. The chambered nautilus shell spirals outward as the creature grows. Each new chamber is larger than the previous one, but the shape remains the same, scaling up proportionally. The spiral approximates the golden spiral that emerges from dividing golden rectangles, the same spiral that appears in the nested pentagons. As the nautilus grows, it maintains its proportions, each chamber related to the previous one by a constant ratio close to the golden ratio. The branching of trees and the arrangement of leaves around stems often follow Fibonacci patterns. Leaves position themselves at angles that maximize their exposure to sunlight and rain, avoiding directly shading lower leaves. The optimal angles involve fractions of complete rotations: 1/2, 1/3, 2/5, 3/8, 5/13, fractions whose numerators and denominators are Fibonacci numbers. These fractions are the rational numbers closest to the golden ratio, providing the most efficient packing arrangements. These patterns arise not because plants perform mathematical calculations, but because the golden ratio represents optimal packing and efficient growth. When a new leaf or floret forms at the growing tip of a plant, it emerges at an angle from the previous one. If this angle is the golden angle, approximately 137.5 degrees, the pattern that emerges naturally minimizes wasted space and maximizes efficiency. Evolution has selected for growth patterns that approximate this ideal, not through understanding but through survival. Plants with more efficient arrangements captured more sunlight, produced more seeds, passed on their growth patterns. The golden ratio appears in the proportions of the human body, though perhaps not as extensively as some Renaissance thinkers believed. The ratio of the height of a person to the height of their navel approximately equals the golden ratio. The ratio of the distance from the shoulder to the fingertips to the distance from the elbow to the fingertips is close to the golden ratio. The bones in the hand, from the knuckles to the fingertips, approximate Fibonacci lengths. These proportions vary among individuals and are only rough approximations. The enthusiasm of some artists and mathematicians to find the golden ratio everywhere led to overstated claims. Not every pleasing proportion involves this ratio. But the tendency of human proportions to cluster around these values reflects developmental patterns in embryonic growth, where structures divide and branch according to genetic instructions that produce approximately exponential scaling. DNA molecules, the fundamental carriers of genetic information, have a double helix structure with dimensions that approximate the golden ratio. The molecule is 21 angstroms wide and completes a full turn every 34 angstroms, both Fibonacci numbers. The ratio between these dimensions is close to the golden ratio. The double helix makes a complete turn every 10 base pairs, and the structure's stability depends on the precise geometry of this spiraling form. Artists and architects throughout history have used the golden ratio, sometimes consciously, sometimes intuitively. The Parthenon in Athens, built between 447 and 432 BCE, has facade proportions that closely approximate the golden rectangle. Whether this was intentional or emerged from aesthetic choices that happened to align with the golden ratio remains debated. The Greeks certainly knew the golden ratio through Euclid's work and earlier Pythagorean studies, so conscious application is possible. Renaissance artists, including Leonardo da Vinci, studied proportion extensively. Da Vinci illustrated Luca Pacioli's book De Divina Proportion, published in 1509, which explored the golden ratio and called it the divine proportion. The book connected this ratio to beauty, harmony, and divine creation. Whether Da Vinci actually used the golden ratio in his paintings remains controversial, with scholars finding evidence both supporting and contradicting its deliberate application. The golden ratio connects geometry, algebra, number sequences, and natural forms. It emerges from pentagons and dodecahedrons, from dividing lines and calculating ratios. It governs the spirals of shells and galaxies, the proportions of molecules and monuments. It is both discovered and created, both observed in nature and constructed by human minds seeking proportion and harmony. The circle is the simplest curve. Take all points in a plane that are exactly the same distance from a single point, and a circle emerges, perfect in its symmetry, uniform in its curvature. The ancient Egyptians and Babylonians knew that the distance around a circle, its circumference, bore a constant relationship to the distance across it, its diameter. But the precise value of this relationship, the number we now call pi, remained elusive, hiding in the gap between straight lines and curves. The circle possesses a purity that other shapes lack. It has no corners, no straight edges, no preferred direction. Every point on its boundary is identical to every other point. Every diameter divides it into two identical halves. Rotate a circle by any amount around its center, and it remains unchanged. This complete rotational symmetry made the circle sacred to ancient cultures, a symbol of perfection, eternity, and the divine. The earliest approximations were rough but useful. The Rhind mathematical papyrus, dating to approximately 1650 BCE, contains a method for finding the area of a circle. The scribe Ames, who copied the papyrus from an earlier source, gave a rule. Take the diameter, subtract 1/9 of it, then square the result. This method implies a value for pi of approximately 3.1605, remarkably close to the true value. The Babylonians, working in their base 60 number system around the same period, used a value of 3.125 for pi. The ancient Indian text Shatapatha Brahmana, composed between 900 and 600 BCE, gives a value of 339/108, which equals approximately 3.139. These ancient mathematicians understood that the relationship was constant, that every circle, regardless of size, had the same ratio between circumference and diameter. These approximations served practical purposes. Building circular structures, calculating areas, dividing land, all could be done adequately with these rough values. Egyptian architects could design circular granaries. Babylonian astronomers could calculate the apparent paths of celestial bodies. The values were good enough for the technology and measurements of the time. But the Greeks wanted more than adequacy. They wanted to know the exact value, or to prove that no exact value existed within their number system. They sought precision not for practical benefit but for the sake of knowledge itself, for the satisfaction of understanding completely. Archimedes of Syracuse, born around 287 BCE, was perhaps the greatest mathematician of antiquity. The stories told about him paint a picture of a man obsessed with geometric problems, drawing figures in the sand, in the ashes of the fire, even in the oil on his own skin after bathing. He would become so absorbed in mathematical contemplation that he forgot to eat, forgot to bathe, had to be carried bodily to the baths by servants. During the Roman siege of Syracuse in 212 BCE, he designed war machines that defended the city for years. Massive catapults hurled stones at Roman ships. Cranes dropped heavy weights onto vessels that came too close to the walls. Mirrors, according to legend, focused sunlight to set ships ablaze, though this particular story is probably apocryphal. The Roman commander Marcellus came to respect and fear the genius defending the city, calling Archimedes a geometrical Briareus, a 100-armed giant from mythology. When Roman soldiers finally breached the walls, Archimedes was studying a geometric figure. A soldier, not recognizing him, killed him, supposedly after Archimedes refused to leave his diagram, crying out, "Do not disturb my circles." Marcellus, who had given orders that Archimedes should be captured alive, was reportedly grieved by his death. He gave Archimedes an honorable burial and placed on his tomb, at Archimedes' own request, a sphere inscribed within a cylinder, representing one of his proudest discoveries about the ratios of their volumes. Archimedes developed a method for approximating pi with unprecedented precision. He began with hexagons, regular six-sided polygons inscribed inside a circle and circumscribed outside it. The perimeter of the inscribed hexagon is less than the circumference of the circle, while the perimeter of the circumscribed hexagon is greater. The true value of pi must lie between the values given by these two hexagons. The inscribed hexagon was relatively easy to calculate. Its perimeter equals 3 times the diameter of the circle, giving a lower bound of 3 for pi. The circumscribed hexagon has a perimeter of approximately 3.464 times the diameter, providing an upper bound. But these bounds were far too loose to be satisfying. Then Archimedes doubled the number of sides, creating 12-sided polygons. These fit the circle more closely, giving tighter bounds on pi. He doubled again to 24 sides, then to 48, then to 96. Each doubling required extensive calculations, finding the side lengths of the new polygons using geometric relationships and the Pythagorean theorem. The mathematical technique was ingenious. Starting from the known side length of a polygon, Archimedes could calculate the side length of a polygon with twice as many sides. The calculation involved square roots and careful algebraic manipulation, all performed without modern notation, using only geometric reasoning and verbal descriptions. After working through the 96-sided polygons, Archimedes concluded that pi is greater than 223/71 and less than 22/7. In decimal notation, this means pi is between 3.1408 and 3.1429. The true value, approximately 3.14159, lies within this range. Archimedes had trapped pi between two rational numbers, squeezing it into an interval less than 3/100ths wide. The upper bound of 22.7 became the standard approximation for pi for centuries. It is accurate to about 0.04%, sufficient for most practical purposes even today. School children still learn 22/7 as a convenient fractional approximation for pi, a testament to Archimedes' work over 2 millennia ago. This method, using polygons with ever-increasing numbers of sides to approximate a circle, became the standard approach for centuries. Chinese mathematician Lu Hui, working around 263 CE, used a polygon with 3,072 sides to calculate pi to approximately 3.14159. By 480 CE, Chinese mathematician Zhu Chongzhi had calculated pi to 7 decimal places, approximately 3.1415927, using a polygon with 24,576 sides. He also found that the ratio 355/113 is an extremely good approximation, accurate to 6 decimal places. Zhu Chongzhi's approximation of 355/113 is remarkably efficient. It requires only 6 digits to remember yet provides 6 decimal place accuracy. No simpler fraction gives better accuracy. This ratio would not be rediscovered in Europe until the 16th century, over 1,000 years after Zhu Chongzhi's work. Arab mathematicians continued this work during the Islamic Golden Age. Al-Khwarizmi, working in Baghdad in the early 9th century, gave a value accurate to 4 digits. By the 15th century, Persian mathematician Jemshid al-Kashi calculated pi to approximately 16 decimal places using a polygon with over 805 million sides, a staggering computational achievement performed without mechanical calculators. Al-Kashi's calculation required years of work and extraordinary computational skill. Each step in doubling the number of polygon sides involved taking square roots, which required iterative approximation methods. The accumulation of these calculations, maintaining accuracy through dozens of doublings, demanded meticulous care. A single error early in the process would corrupt all subsequent results. But pi resisted all attempts to express it exactly as a fraction or finite decimal. The number goes on forever without repeating. 3.1415926538979323846. The digits follow no discernible pattern. The number seems to wander randomly, each new digit unpredictable from those before it. Mathematicians calculated more and more digits, hoping to find a pattern, a repetition, some key to understanding its structure. But none emerged. The circle's circumference divided by its diameter yields an irrational number, a number that cannot be expressed as a ratio of integers. This was proven in 1761 by Johann Heinrich Lambert, a German mathematician and physicist. His proof showed that if you assume pi is rational and express it as a fraction, you arrive at a logical contradiction. Therefore, pi must be irrational. Lambert's proof used continued fractions, infinite expressions that represent numbers as sums of fractions within fractions. He showed that the continued fraction for the tangent function has a specific form, and from this proved that tan x and arctan x are irrational when x is a non-zero rational number. Since tan pi/4 equals 1, a rational number, pi/4 must be irrational, and therefore pi itself is irrational. But pi is stranger than merely irrational. In 1882, German mathematician Ferdinand von Lindemann proved that pi is transcendental, meaning it is not the solution to any polynomial equation with rational coefficients. While the square root of 2 is irrational, it is the solution to the equation x squared equals 2. Pi is not the solution to any such equation, no matter how complex. Transcendental numbers are, in a sense, more irrational than algebraic irrationals. Algebraic numbers, even irrational ones like the square root of 2, can be captured by polynomial equations. They have a finite description in terms of basic arithmetic operations and root extractions. Transcendental numbers escape this finite characterization. They cannot be constructed through any finite sequence of arithmetic operations applied to rational numbers. This proof finally resolved one of the oldest problems in mathematics: squaring the circle. The ancient Greeks had sought to construct, using only a compass and straightedge, a square with the same area as a given circle. Many attempted this construction. Some claimed success, though careful analysis always revealed subtle errors. Lindemann's proof showed the task was impossible. Since pi is transcendental, it cannot be constructed using compass and straightedge, and therefore neither can a square with area equal to a given circle. The impossibility of squaring the circle was not immediately accepted by everyone. Amateur mathematicians continued to submit claimed solutions well into the 20th century. The problem had become so notorious that many mathematical journals adopted policies refusing to consider any more submissions on the subject. But Lindemann's proof was rigorous and complete. The circle could not be squared. A 2,000-year quest had ended not in success but in proof of impossibility. Pi appears throughout mathematics, far beyond its original definition in terms of circles. It emerges in probability theory, in the bell curve that describes random variations. The formula for the normal distribution involves pi in its denominator, connecting the geometry of circles to the statistics of random events. This connection arises because the derivation of the normal distribution involves calculating areas under curves, integrating exponential functions, and the results naturally involve pi. Pi appears in number theory in formulas involving prime numbers. The Basel problem, solved by Euler in 1734, asks for the sum of the reciprocals of the squares. 1 plus 1/4 plus 1/9 plus 1/16 plus. Remarkably, this sum equals pi superscript 2/6. The connection between prime numbers, represented through their distribution, and pi seems mysterious, yet it emerges from deep properties of the Riemann zeta function. It shows up in complex analysis, in equations describing waves and oscillations. The sine and cosine functions, which describe periodic phenomena from sound waves to planetary orbits, are intimately connected to pi. A complete oscillation, a full cycle, corresponds to an angle of 2 pi radians. The functions themselves can be defined through infinite series involving powers of pi. The Euler identity, discovered by Swiss mathematician Leonhard Euler in the 18th century, connects pi with the exponential function and the imaginary unit, e raised to the power of pi times the imaginary unit equals -1. This equation links 5 of the most important numbers in mathematics: 0, 1, e, I, and pi, binding together seemingly unrelated areas of mathematical thought. This identity has been called the most beautiful equation in mathematics. It connects arithmetic through 0 and 1, algebra through I, the imaginary unit, analysis through e, the base of natural logarithms, geometry through pi, and equality itself. That such disparate concepts should meet in such a simple, elegant equation suggests a deep underlying unity to mathematics. Pi connects the discrete and the continuous, the straight and the curved, the rational and the irrational. It is defined by the simplest possible curve yet contains infinite complexity. Every sequence of digits, no matter how long, eventually appears somewhere in pi's infinite expansion. Every possible number is encoded within it, hidden in its endless, patternless progression. This property, if true, means that pi contains every message ever written and every message that ever will be written, encoded somewhere in its digits. Your name, your birthday, your entire genetic sequence, the complete text of every book, all exist somewhere in the infinite digits of pi. The property has not been rigorously proven, but computational explorations of trillions of digits support it. Modern computers have calculated pi to trillions of digits. The current record exceeds 100 trillion decimal places, calculated using sophisticated algorithms far more efficient than the polygon method of Archimedes. These calculations serve partly as tests of computer hardware and partly from pure curiosity, the human desire to see further into the infinite. The circle, that ancient symbol of perfection and eternity, guards within its geometry a number that embodies the infinite, the irrational, the transcendent. The Egyptians who first measured circular fields could not have imagined that they were touching something that would resist complete understanding for thousands of years, a number that would reveal the limits of what can be constructed, what can be expressed, what can be fully known. The planets wander. Unlike the fixed stars that maintain their patterns night after night, the planets move against the stellar background, tracing paths that seem to loop and reverse, advancing and retreating in their journeys across the sky. Ancient astronomers watched these wandering stars for thousands of years, recording their positions, seeking patterns in their motions. Pythagoras, or perhaps his followers, proposed that the Earth was spherical rather than flat, arguing from geometric principles and observations. A sphere was the perfect shape, symmetric from every direction. The shadow the Earth cast on the Moon during lunar eclipses was always circular, regardless of the time or season. Ships disappeared hull first over the horizon, as if descending over a curved surface. Aristotle, in the 4th century BCE, provided additional arguments for Earth's sphericity. The North Star appeared higher in the sky as one traveled north and lower as one traveled south. Different stars became visible from different latitudes. The only shape that could produce these observations was a sphere. but Aristotle placed this spherical Earth at the center of the cosmos. The sun, moon, planets, and stars all revolved around Earth in perfect circles. Circular motion was natural for celestial objects, he argued, eternal and unchanging, fitting for the incorruptible heavens. This geocentric model faced immediate difficulties. The planets did not move in simple circles. They would advance across the sky, then slow, stop, reverse direction for a time, then resume their forward motion. This retrograde motion contradicted the idea of simple circular paths centered on Earth. Apollonius of Perga, around 200 BCE, proposed a solution. Imagine that each planet moves in a small circle called an epicycle, and the center of this epicycle moves along a larger circle called a deferent centered on Earth. As the planet circles the epicycle, and the epicycle center moves along the deferent, the combined motion can produce the observed patterns, including periods of retrograde motion. Hipparchus of Nicaea, working in Rhodes around 130 BCE, refined this model further. He created the first comprehensive star catalog, recording the positions of approximately 850 stars with unprecedented precision. He discovered the precession of the equinoxes, a slow rotation of Earth's axis that causes the positions of the stars to shift gradually over thousands of years. Hipparchus also introduced the concept of the eccentric, placing the center of a circular orbit not at Earth's center but at a point offset from it. This simple geometric modification allowed the model to match observations more closely while maintaining the principle of circular motion. These systems were synthesized by Claudius Ptolemy, who worked in Alexandria around 150 CE. His treatise, later known by its Arabic name Almagest, presented a complete geometric model of the cosmos. Ptolemy combined epicycles, deferents, eccentrics, and another innovation called the equant, a point from which the angular motion of the epicycle center appeared uniform, even though the actual speed varied. The Ptolemaic system was complex, requiring dozens of circles to account for the observed motions of the sun, moon, and 5 visible planets. But it worked. It could predict planetary positions with reasonable accuracy, calculate the times of eclipses, and explain the changing brightness of planets as they moved closer to and farther from Earth. For nearly 1,500 years, this geometric model dominated astronomical thought. It aligned with philosophical and theological views that placed humanity at the center of creation. It fit with the Aristotelian physics that dominated medieval universities. It matched everyday experience. The Earth seemed stationary. The sun appeared to move across the sky. But there were problems. The model required constant adjustments to match improving observations. The multiplicity of circles seemed inelegant, a patchwork of geometric fixes rather than a unified understanding. And there was a philosophical tension. The equant violated the principle of uniform circular motion that the entire system was meant to preserve. In 1543, as he lay on his deathbed, Polish astronomer Nicholas Copernicus received a copy of his newly published book De Revolutionibus Orbium Coelestium on the revolutions of the celestial spheres. In this work, Copernicus proposed a radical revision of cosmic geometry. The Sun, not Earth, was the center of the cosmos. Earth was a planet like the others, orbiting the Sun and rotating on its axis daily. This heliocentric model immediately explained retrograde motion without epicycles. When Earth, moving along its orbit, overtakes a slower outer planet, that planet appears to move backward against the stars, just as a car being overtaken appears to move backward relative to a faster car. Copernicus retained circular orbits and still needed some epicycles to match observations precisely. His system was not dramatically simpler than Ptolemy's in terms of the number of circles required, but it possessed a conceptual unity that the geocentric model lacked. The planets' periods of revolution increased with their distance from the Sun. The sizes of the planetary orbits were no longer arbitrary but were determined by observations and geometric relationships. The Copernican model initially attracted little attention and considerable opposition. It contradicted scripture passages that spoke of the Sun moving. It violated Aristotelian physics, which held that Earth was naturally at rest and that circular motion was natural only for celestial objects, not for Earth itself. And it made the starry sphere vastly larger, since the lack of observed stellar parallax, the apparent shift in stars' positions as Earth moved in its orbit, required the stars to be at enormous distances. Danish astronomer Tycho Brahe, working in the late 16th century, produced the most accurate observations of planetary positions ever made without telescopes. He could not accept the heliocentric model, proposing instead a hybrid system where the planets orbited the Sun, but the Sun orbited Earth. After Tycho's death in 1601, his assistant Johannes Kepler inherited these precious observations. Kepler, a German mathematician and mystic, was convinced of the heliocentric model but struggled to make it match Tycho's data. He focused on Mars, whose motion was particularly difficult to model accurately. For years, he tried to fit circular orbits to the observations, adjusting the size and speed and orientation of Mars's orbit. He could get close, but there were always discrepancies of 8 arc minutes, about a quarter of the Moon's apparent diameter. A less careful observer might have ignored this small difference, but Kepler trusted Tycho's measurements. If the observations disagreed with his model by 8 arc minutes, the model was wrong. In 1605, after exhaustive calculations, Kepler abandoned the circle. The orbit of Mars, Kepler discovered, was an ellipse, one of the conic sections studied by Apollonius 2,000 years earlier. An ellipse is like a stretched circle with 2 focal points instead of a single center. The Sun occupies one of these foci, and Mars orbits along the elliptical path with the Sun off-center, closer to one side of the orbit than the other. This was revolutionary. For 2 millennia, from Pythagoras through Ptolemy and Copernicus, circles had been the foundation of celestial geometry. Circular motion was perfect, eternal, divinely ordained. Kepler's ellipse violated this ancient principle, replacing cosmic perfection with a shape that seemed less ideal, less symmetric. But the ellipse matched observations perfectly. Kepler published this discovery as his first law of planetary motion in 1609. Planets orbit the Sun in elliptical paths with the Sun at one focus. Kepler also discovered that planets move faster when closer to the Sun and slower when farther away, but in a precise way. If you draw a line from the Sun to a planet, this line sweeps out equal areas in equal times. A planet in the part of its orbit closer to the Sun covers more distance in a given time than when it is farther away, but the area swept out remains constant. This was his second law. 10 years later, Kepler published his third law. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This revealed a deep mathematical relationship connecting the size and timing of planetary orbits, a harmony not of perfect circles but of ellipses and square and cube relationships. The geometry of the heavens was stranger and more beautiful than the ancients had imagined. The cosmic dance followed not the rigid perfection of circles but the more subtle perfection of ellipses, conic sections that emerged from slicing a cone, geometric forms that Apollonius had studied for purely theoretical reasons centuries before they revealed their role in the architecture of the solar system. René Descartes sat in his room on a cold morning in November 1619, watching a fly walk across the ceiling. The young French philosopher and mathematician, then 23 years old, observed how the fly's position could be described by measuring its distance from two adjacent walls. Every point on the ceiling corresponded to a unique pair of distances, and every pair of distances identified a unique point. This observation, whether it occurred exactly this way or has been embellished by time, led to one of the most important developments in mathematical history. Descartes realized that points in space could be represented by numbers, and geometric shapes could be described by algebraic equations. Geometry and algebra, two separate branches of mathematics since ancient times, could be unified. In 1637, Descartes published La Géométrie as an appendix to his philosophical work Discourse on Method. In this treatise, he introduced a coordinate system, now called Cartesian coordinates, in his honor. Two perpendicular lines called axes define a plane. Every point in the plane can be located by two numbers, its distances from the two axes, measured in perpendicular directions. A circle centered at the origin with radius r can be described by the equation x squared plus y squared equals r squared, where x and y are the coordinates of any point on the circle. This equation is simply the Pythagorean theorem applied to the right triangle formed by the point, its projections on the axis, and the origin. A line can be described by an equation like y equals mx plus b, where m determines the line's slope and b determines where it crosses the vertical axis. Different values of m and b produce different lines, and every line in the plane corresponds to some values of these two parameters. Curves that had been studied separately, described in purely geometric terms, could now be expressed as equations. The ellipse, the parabola, the hyperbola, all those conic sections that Apollonius had investigated, became algebraic formulas. An ellipse centered at the origin with semi-axes a and b satisfies the equation x squared over a squared plus y squared over b squared equals 1. This unification allowed geometric problems to be solved using algebraic techniques and algebraic problems to be understood geometrically. A system of two linear equations with two unknowns corresponds to two lines in a plane. The solution to the system, if it exists, is the point where the lines intersect. If the lines are parallel, there is no solution. If the lines coincide, there are infinitely many solutions. Descartes' coordinate system transformed mathematics, but it was only part of a larger revolution in understanding change and motion. The ancient Greeks had mastered static geometry, the relationships between fixed shapes and figures, but motion and continuous change resisted their methods. Zeno of Elea in the 5th century BCE had posed paradoxes about motion that troubled philosophers for centuries. In his most famous paradox, Achilles races a tortoise. The tortoise gets a head start. Before Achilles can overtake the tortoise, he must reach the point where the tortoise started. But by the time he reaches that point, the tortoise has moved forward. Achilles must then reach this new point, but again the tortoise has advanced. This process continues infinitely. How then, Zeno asked, can Achilles ever overtake the tortoise? The paradox arises from dividing motion into infinite steps. Each step takes time, so infinitely many steps should take infinite time. Yet in reality, Achilles easily overtakes the tortoise. The resolution requires understanding how an infinite series of decreasing numbers can sum to a finite value, a concept that was not rigorously formulated in ancient times. Archimedes had approached such questions with his method of exhaustion, approximating areas and volumes by filling them with simple shapes. But he worked with specific geometric figures, developing clever arguments for each particular case. What was needed was a general method, a systematic approach to measuring change and accumulation. In the mid-17th century, Pierre de Fermat and Blaise Pascal developed methods for finding tangents to curves, lines that just touch a curve at a single point without crossing it. The slope of the tangent represents the rate of change of the curve at that point, the instantaneous direction of motion if the curve represents a path through space. Finding tangents required a subtle idea. To compute the slope of a line through 2 points on a curve, you calculate the rise over the run, the change in vertical position divided by the change in horizontal position. But for a tangent at a single point, you need the slope through 2 points that coincide, the change over zero change, which seems meaningless. The solution was to consider what happens as the 2 points get closer together. Calculate the slope through 2 nearby points, then imagine bringing them closer and closer, letting the distance between them approach zero. The slopes approach a limiting value, and this limit is the slope of the tangent. Isaac Newton, working in England in the 1660s, and Gottfried Wilhelm Leibniz, working independently in Germany in the 1670s, developed complete systems for handling such limiting processes. They created calculus, a mathematical framework for studying continuous change, rates, accumulations, and the relationships between them. Newton called his method the calculus of flux ions. He imagined quantities flowing in time, continuously changing, and sought to understand their instantaneous rates of change. If x represents position, its rate of change with respect to time is velocity. The rate of change of velocity is acceleration. Leibniz developed similar ideas with different notation, using the concepts of differentials, infinitesimally small increments in quantities. His notation, using the symbols d and the integral sign, proved more flexible and intuitive, and is the notation still used today. The fundamental insight of calculus is that two types of problems, seemingly different, are actually inverses of each other. Given a curve, you can find its instantaneous rate of change at each point, its derivative. Given a rate of change, you can reconstruct the original quantity by accumulation by integration. Differentiation and integration are reverse processes, two sides of the same mathematical coin. Newton used calculus to solve the ancient problem of planetary motion. Kepler had described how planets move, but not why. Newton's law of universal gravitation stated that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Using calculus, Newton proved that this inverse square law of gravity produces exactly the elliptical orbits that Kepler had discovered. The geometric paths of planets emerged necessarily from the mathematical law of force, combined with the calculus of motion and change. Newton's Philosophiae Naturalis Principia Mathematica, published in 1687, unified terrestrial and celestial mechanics, showing that the same geometric principles and physical laws govern both falling apples and orbiting planets. Calculus also enabled the precise measurement of curved lines, areas bounded by curves, and volumes of irregular solids. Problems that had required individual ingenuity and clever geometric arguments could now be solved systematically using standard techniques. The area under a curve from one point to another could be calculated by integration. The length of a curve could be found using the Pythagorean theorem applied to infinitesimal segments and adding them up through integration. Volumes of revolution, shapes formed by rotating a curve around an axis, yielded to systematic calculation. Geometry was no longer confined to static relationships between fixed forms. It now encompassed motion, growth, change, accumulation. Every smooth curve had a tangent at every point, representing its instantaneous direction. Every bounded region had an area that could be computed. The continuous variation of quantities could be analyzed mathematically, revealing patterns and relationships invisible to earlier methods. The differential geometry developed in subsequent centuries showed that space itself could be studied using calculus. Curves could be characterized by their curvature at each point, how sharply they bend. Surfaces could be measured by their Gaussian curvature, a quantity that describes whether they curve like a sphere, like a saddle, or remain flat like a plane. These developments transformed geometry from a study of specific shapes into a general framework for understanding continuity, smoothness, and change. The rigid figures of Euclid's elements remained valid and important, but they were now seen as special cases within a vast landscape of possible forms, all amenable to analysis through the powerful methods of calculus. For 2,000 years, Euclid's fifth postulate troubled mathematicians. The first four postulates were simple, self-evident, impossible to doubt. A straight line can be drawn between any 2 points. A straight line can be extended. A circle can be drawn with any center and radius. All right angles are equal. But the fifth postulate, the parallel postulate, was different. It was longer, more complicated, less obviously true. It stated that if a line crosses two other lines and makes the interior angles on one side sum to less than two right angles, then those two lines, if extended far enough, will eventually meet on that side. This was equivalent to saying that through a point not on a given line, exactly one line can be drawn parallel to the given line. The statement seemed true, matched all experience, and was essential for proving many of Euclid's theorems. But it did not possess the immediate self-evidence of the other postulates. For centuries, mathematicians tried to prove the parallel postulate from the first four, believing it should be a theorem rather than an axiom. If it could be derived from simpler, more obvious principles, the foundations of geometry would be more secure. Proclus, a 5th century Greek mathematician, attempted a proof. Islamic mathematicians during the medieval period made numerous attempts. Renaissance and early modern mathematicians continued the effort. Every proposed proof eventually revealed a hidden flaw, typically an assumption equivalent to the parallel postulate itself, smuggled into the argument without recognition. The postulate resisted derivation, maintaining its status as an independent assumption. In the 18th century, Italian mathematician Giovanni Girolamo Saccari tried a different approach. He assumed the first four postulates were true but supposed the parallel postulate was false. He hoped to derive a logical contradiction, thereby proving indirectly that the parallel postulate must be true. Saccari investigated two alternatives. Either there are no lines through a point parallel to a given line, or there are multiple such lines. He developed the logical consequences of these assumptions, expecting to find impossibilities. Instead, he found strange but logically consistent geometries, worlds where the rules of space were different from Euclidean geometry but not contradictory. In his 1733 book Euclid's Ob Omni Naivo Vindicatus, Euclid freed from every flaw, Saccari convinced himself he had found contradictions and thus vindicated Euclid. But his arguments were flawed, and what he had actually discovered, without fully recognizing it, were the first glimpses of non-Euclidean geometry. The breakthrough came in the 19th century, independently discovered by three mathematicians: Carl Friedrich Gauss in Germany, János Bolyai in Hungary, and Nikolai Lobachevsky in Russia. Each realized that consistent geometries could exist where the parallel postulate fails. Lobachevsky published his findings first in 1829 and 1830, describing a geometry where through a point not on a given line, infinitely many lines can be drawn that never intersect the given line. This hyperbolic geometry, as it came to be called, had strange properties. The angles of a triangle sum to less than 180 degrees, and the larger the triangle, the smaller this sum. Parallel lines diverge from each other rather than maintaining a constant distance. Bolyai, working independently, arrived at similar conclusions and published them in 1832 as an appendix to his father's mathematical work. His father, Farkas Bolyai, had spent years trying to prove the parallel postulate and warned his son against pursuing this mathematical quicksand. But János succeeded where his father had failed, creating a consistent alternative geometry. Gauss had discovered these ideas earlier, probably by the 1820s, but never published them. He feared controversy, knowing how radical the ideas were. In a letter written in 1824, he mentioned his belief that the geometry of physical space might not be Euclidean, that whether the angles of a triangle sum to exactly 180 degrees was an empirical question to be settled by measurement, not a necessary truth of pure reason. Gauss even conducted an experiment, measuring the angles of a triangle formed by 3 mountain peaks. The measurements were consistent with Euclidean geometry within experimental error, but Gauss recognized this did not prove Euclidean geometry was necessarily true, only that any deviation was small enough to be undetectable at the scale of his measurements. A different type of non-Euclidean geometry emerged from considering spherical surfaces. On a sphere, the shortest path between 2 points is a great circle, a circle whose center coincides with the sphere's center. Great circles play the role of straight lines in spherical geometry. But on a sphere, there are no parallel lines. Any 2 great circles intersect at 2 antipodal points. The angles of a triangle sum to more than 180 degrees, and the larger the triangle, the greater this sum. A triangle can even have 3 right angles, something impossible in Euclidean geometry. This elliptic geometry, as it is called, was studied by German mathematician Bernhard Riemann in the mid-19th century. Riemann generalized the concept of geometry itself, showing how to define geometric properties, like distance and curvature, on any smooth surface or even in higher dimensional spaces. Riemann's approach was abstract and powerful. He did not start with specific shapes or particular axioms. Instead, he defined geometry through a metric, a mathematical formula that determines the distance between nearby points. Different metrics produce different geometries, all equally valid mathematically, differing in their properties but not in their logical consistency. This revealed that Euclidean geometry was not the only possible geometry, not the geometry decreed by logic or divine order, but one geometry among infinitely many. The parallel postulate was not a truth that must be proven, but an assumption that defines which geometry you are working in. Assume the parallel postulate and you get Euclidean geometry. Assume its denial in one way and you get hyperbolic geometry. Deny it differently and you get elliptic geometry. The discovery of non-Euclidean geometry shook the foundations of mathematical and philosophical thought. Kant had argued that Euclidean geometry was synthetic a priori knowledge, true by the very structure of human cognition, a necessary framework through which the mind organizes experience. But if multiple consistent geometries exist, this position becomes untenable. The geometry of physical space becomes an empirical question. Which geometry describes the actual universe we inhabit? At human scales, in everyday experience, space appears Euclidean. But perhaps at very large scales or in strong gravitational fields, space curves in ways that require non-Euclidean geometry. This question remained philosophical speculation until Albert Einstein developed general relativity in 1915. Einstein's theory describes gravity not as a force but as curvature of spacetime. Mass and energy curve the geometry of space and time around them, and objects move along the straightest possible paths, called geodesics, through this curved geometry. In general relativity, The geometry of space is not fixed but dynamically determined by the distribution of matter and energy. Near massive objects like stars, space curves, and light follows curved paths through this warped geometry. The universe as a whole has a geometry that depends on its total mass and energy density. If the density exceeds a critical value, space curves back on itself, forming a closed finite geometry like the surface of a sphere. If the density is less, space has a hyperbolic geometry, extending infinitely in all directions. Observations of distant supernovae, the cosmic microwave background radiation, and the large-scale structure of galaxies suggest that the universe is very close to flat, with a geometry that is Euclidean or very nearly so at the largest scales. But the theoretical framework allows for non-Euclidean geometries and local regions of space-time near massive objects or in extreme conditions definitely exhibit non-Euclidean properties. The geometry of the universe is written in the distribution of matter and energy, in the curvature of space-time around galaxies and black holes. The ancient question of what parallel lines do, whether they remain forever equidistant or eventually converge or diverge, has an answer that depends on where you are and what matter surrounds you. Geometry has become physics, and the shape of space itself has become a subject of scientific investigation. This mathematical framework proved essential for Einstein's general relativity. Spacetime has 4 dimensions, 3 of space and 1 of time. Events are points in this 4-dimensional spacetime, specified by 3 spatial coordinates and 1 time coordinate. The geometry of spacetime curves in the presence of mass and energy, and this curvature manifests as gravity. The equations of general relativity involve the metric tensor, a mathematical object that encodes how distances are measured in curved 4-dimensional spacetime. This metric determines the paths that objects follow, the way light bends near massive bodies, the slowing of time in strong gravitational fields. All these phenomena emerge from the geometry of 4-dimensional spacetime. Later in the 20th century, physicists investigating theories that might unify gravity with quantum mechanics proposed that space might have more than 3 dimensions. String theory, developed in the 1960s and extensively in the 1980s, suggests that fundamental particles are not points but tiny loops of vibrating string. The mathematics of string theory requires spacetime to have 10 dimensions, or in some versions 11. Where are these extra dimensions? The proposal is that they are compactified, curled up on themselves at scales far too small to detect directly. Imagine a garden hose viewed from far away. It appears one-dimensional, a line, but an ant walking on the hose has 2 dimensions available, along the length of the hose and around its circumference. The circumferential dimension is invisible at large scales but real and traversable at small scales. Similarly, if 6 or 7 spatial dimensions are compactified, curled up with radii smaller than the smallest distances we can probe, they would be invisible in ordinary experience. But they would influence the physics of fundamental particles, determining the properties of matter and the strengths of forces through the geometry of these hidden dimensions. These ideas remain speculative, awaiting experimental confirmation, but they demonstrate how geometric thinking extends beyond 3 dimensions, how mathematical consistency allows for spaces of any dimensionality, each with its own properties and structures. Topology, the study of properties preserved under continuous deformations, provides another window into higher dimensions. A coffee cup and a donut are topologically equivalent because one can be continuously deformed into the other without tearing or gluing. Both have a single hole, but a sphere is topologically distinct from a donut, having no holes. In 3 dimensions, there are infinitely many topologically distinct surfaces. But the Poincaré conjecture, posed in 1904 and finally proven by Grigori Perelman in 2003, classified 3-dimensional spaces, showing that any simply connected, closed 3-dimensional space is topologically equivalent to a 3-dimensional sphere. Higher dimensions have their own topological properties, their own catalogs of possible shapes and structures. 4-dimensional space is particularly interesting, exhibiting phenomena that occur in no other dimension. Some knots that cannot be untangled in 3 dimensions can be untangled in 4 dimensions, as the extra dimension provides room to maneuver. Other topological structures exist only in specific dimensions, depending on the particular constraints and freedoms that dimensionality provides. The study of higher dimensional geometry has become essential in modern mathematics and physics, a natural extension of the geometric thinking that began with measuring fields in ancient Egypt. Dimensions beyond sight are not mystical or metaphysical but mathematical, defined precisely, explored logically, revealing structures and relationships as real, in their own way, as the 3 dimensions we move through daily. In the closing years of the 19th century, George Cantor sat in his study in Halle, Germany, writing letters to fellow mathematicians, defending ideas that many considered incomprehensible or even heretical. Cantor had discovered that infinity was not a single concept but came in different sizes, that some infinite collections contained more elements than others, and that these different infinities could be compared and ordered. His colleagues resisted. Leopold Kronecker, an influential German mathematician, argued that only finite, constructible objects were truly mathematical. He called Cantor's work mathematical mysticism and blocked his career advancement. But Cantor persisted, developing a rigorous theory of infinite sets that would eventually revolutionize mathematics. The simplest infinity is the size of the natural numbers, 1, 2, 3, 4, continuing forever. Cantor called this cardinality Aleph null. Any collection that can be put into one-to-one correspondence with the natural numbers has this cardinality, is countably infinite. Surprisingly, the even numbers are countably infinite. Though they seem to be only half the natural numbers, they can be paired with all natural numbers. 1 with 2, 2 with 4, 3 with 6, and so on. Every natural number has a corresponding even number, and vice versa. The 2 sets have the same size of infinity. The rational numbers, all fractions of whole numbers, are also countably infinite. This seems more surprising, as between any 2 fractions there are infinitely many more fractions. Yet Cantor showed how to list all positive fractions in a sequence. First fractions with numerator and denominator summing to 2, then summing to 3, then 4, arranging them systematically so every fraction eventually appears. This demonstrates that despite their density, the rationals can be paired with natural numbers. But the real numbers, all possible decimals, are uncountably infinite. Cantor proved this using a diagonal argument. Suppose all real numbers between 0 and 1 could be listed. Write them as infinite decimals in a sequence. Now construct a new decimal. For its first digit after the decimal point, choose something different from the first digit of the first number in the list. For its second digit, choose something different from the second digit of the second number. Continue this process. The resulting decimal differs from every number in the list in at least one position. Therefore, it's not in the list. But the list was supposed to contain all real numbers, a contradiction. The conclusion is that no such list can exist. The real numbers cannot be counted, even with an infinite counting process. They form a larger infinity than the natural numbers. This has geometric implications. A line segment containing all real numbers between 2 points has uncountably many points. Yet a plane, two-dimensional and seemingly vaster, also contains uncountably many points. Are they the same size of infinity? Cantor proved they are. He showed how to pair each point on a line segment with a unique point in the plane, and vice versa. The technique involves interleaving the digits of two coordinates. A point in the plane has two coordinates, each an infinite decimal. Create a single infinite decimal by alternating digits from the two coordinates. First digit of first coordinate, first digit of second coordinate, second digit of first coordinate, and so on. This creates a one-to-one correspondence between the plane and the line. This result shocked mathematicians. The plane seems infinitely larger than a line, having an extra dimension. Yet both contain the same size of infinity of points. Dimension does not affect the cardinality of points in continuous spaces. The same argument extends to three dimensions for dimensions any number of dimensions. All have the same cardinality of points as a single line segment. Infinity absorbs dimensionality, rendering it irrelevant to counting. But are there infinities larger than the cardinality of the real numbers? Cantor proved there are. Given any set, the collection of all its subsets, called its power set, always has greater cardinality. The power set of the natural numbers has the same cardinality as the real numbers. The power set of the real numbers has an even larger cardinality. This process continues infinitely, generating an endless hierarchy of larger and larger infinities. Cantor conjectured that no cardinality exists between Aleph null and the cardinality of the real numbers. This statement, called the continuum hypothesis, became one of the most famous unsolved problems in mathematics. In 1900, David Hilbert presented a list of 23 unsolved problems at the International Congress of Mathematicians in Paris. The continuum hypothesis was the first. Hilbert believed mathematics should be able to prove or disprove any well-formed mathematical statement. Discovering which answer was correct was just a matter of finding the right approach. But in 1931, Kurt Gödel proved his incompleteness theorems, showing that any consistent mathematical system powerful enough to describe arithmetic contains statements that are true but cannot be proven within the system. Mathematics, Gödel showed, is fundamentally incomplete. There will always be true statements that escape proof. In 1940, Gödel proved that the continuum hypothesis cannot be disproved from the standard axioms of set theory. In 1963, Paul Cohen proved it cannot be proved either. The continuum hypothesis is independent of the axioms, neither provable nor disprovable, can be assumed true or false, and either assumption leads to a consistent mathematics. This revelation transformed understanding of mathematical truth. Mathematics is not a single, necessary structure but a collection of possible structures, different depending on which axioms are chosen. The geometry of infinite sets, the sizes of different infinities, depend on foundational assumptions that logic alone cannot settle. Fractals provided another perspective on geometric infinity. Benoit Mandelbrot, working in the 1970s and 1980s, studied shapes with fractional dimensions, objects that are more than lines but less than surfaces, more than surfaces but less than solids. The coastline of Britain, Mandelbrot observed, has no well-defined length. Measured with a 1-kilometer ruler, walking it and counting ruler lengths gives one result. Using a 1-meter ruler gives a longer result, as the smaller ruler captures more detail, more inlets and outcroppings. A centimeter ruler gives an even longer result. As the ruler length decreases, the measured coastline length increases without bound, approaching infinity. This is because coastlines are self-similar at multiple scales. Zoom in on a section and you see similar complexity as the whole. Zoom in further and the pattern repeats. The coastline has detail at all scales, infinite complexity, a dimension between 1 and 2. The Mandelbrot set, a famous fractal generated by a simple mathematical formula, exhibits infinite complexity. Zoom into its boundary and intricate patterns appear. Zoom further and new structures emerge, spirals, tendrils, miniature copies of the whole set, never-ending variation and detail. The boundary has infinite length, despite enclosing a finite area. Fractals appear throughout nature. The branching of trees, the structure of lungs, the tributaries of rivers, the distribution of galaxies, all exhibit self-similarity across scales. Nature uses fractal geometry to maximize surface area, to pack complexity into finite spaces, to create structures that are efficient at all scales simultaneously. The geometry of infinity reveals that space contains far more structure than finite measurements suggest. Between any 2 points on a line lie infinitely many other points. Within any finite region lie uncountably many positions. Curves can have infinite length while bounding finite areas. Surfaces can have infinite area while enclosing finite volumes. Space is inexhaustible, containing unlimited complexity within the smallest regions, endless detail in every direction, dimensions and structures beyond direct perception but accessible to mathematical thought. In the winter of 1611, Johannes Kepler observed snowflakes falling in Prague. Each one was unique in its detailed structure, yet all shared the same basic form. 6-fold symmetry, 6 points or 6 branches, angles and shapes that repeated around a central point. Why, Kepler wondered, did snowflakes always have 6 sides, never 5 or 7? Kepler wrote a small treatise, The 6-Cornered Snowflake, exploring this question. He considered the geometry of packing, how spheres or circles arrange themselves when compressed together. 6 circles of equal size fit perfectly around a central circle of the same size, all touching. This hexagonal packing is the most efficient way to fill a plane with circles, leaving the least wasted space. Perhaps, Kepler speculated, the crystalline structure of ice reflects this optimal packing geometry. Water molecules arrange themselves into a regular pattern, and the macroscopic form of the snowflake reveals the microscopic geometry of its construction. Kepler could not see molecules or atomic structures. The tools for such observation would not exist for another 3 centuries. But his geometric intuition was correct. Ice crystals have a hexagonal structure at the molecular level, and this microscopic geometry determines the macroscopic shape of snowflakes. Crystals had fascinated humans for millennia. Ancient peoples prized them for their beauty and regularity, their flat faces meeting at precise angles, their internal order evident in their external form. Quartz crystals form perfect hexagonal prisms terminated by pyramidal points. Salt crystals are cubes. Diamond crystals are octahedrons, eight-sided figures bounded by equilateral triangles. In 1669, Danish scientist Nicholas Steno studied quartz crystals and discovered that the angles between corresponding faces were always the same, regardless of the crystal size or the exact shape of the faces. This law of constant angles suggested that crystals have an underlying regular structure, a geometric order that determines their form. French mineralogist René Just Houy, working in the late 18th century, proposed that crystals are built from tiny identical units stacked together in regular arrays. He envisioned these units as parallelepipeds, box-like shapes that tile space perfectly. Different arrangements of these basic units could produce different crystal forms. The concept was prescient, though Houy imagined the units as solid blocks rather than arrangements of atoms. Nevertheless, he correctly identified the key principle. Crystals are periodic structures, patterns that repeat regularly in space. In 1848, French physicist Auguste Bourgeois classified all possible ways to arrange points in a regular three-dimensional lattice. He found exactly 14 distinct types, now called Bourgeois lattices. Every crystal structure can be described as a particular Bourgeois lattice with atoms or molecules positioned at the lattice points and possibly at other locations with fixed relationships to those points. The Bourgeois lattices include simple cubic, body-centered cubic, face-centered cubic, hexagonal, and various others. Each has different symmetries, different angles and distances, but all share the property of translational symmetry. The pattern repeats identically as you move along certain directions. Crystals also exhibit rotational symmetry. A cube looks the same after rotating 90 degrees around an axis through its center. A hexagonal crystal looks the same after rotating 60 degrees. But not all rotational symmetries are possible in crystals. In 2 dimensions, periodic patterns can have 2-fold, 3-fold, 4-fold, or 6-fold rotational symmetry. These correspond to rotations of 180, 120, 90, or 60 degrees, leaving the pattern unchanged. But 5-fold symmetry is impossible in a periodic pattern that tiles the plane. No arrangement of identical regular pentagons can fill a plane without gaps. This crystallographic restriction applies in 3 dimensions as well. Periodic crystal structures can have 1-fold, 2-fold, 3-fold, 4-fold, or 6-fold rotational axes, but not 5-fold and not any higher than 6-fold. This seems to be a fundamental limitation of geometry, a restriction on how space can be filled with repeating patterns. In 1912, German physicist Max von Laue and his collaborators discovered that crystals diffract X-rays in specific patterns. X-rays have wavelengths comparable to the spacing between atoms in crystals. When X-rays pass through a crystal, they scatter from the regular array of atoms, creating interference patterns that reveal the crystal's internal structure. X-ray crystallography became a powerful tool for determining atomic arrangements. William Henry Bragg and his son William Lawrence Bragg developed the mathematical relationship between the angles at which X-rays are diffracted and the spacing of atomic planes in the crystal. Their work, published in 1913, enabled the precise determination of crystal structures. Over the following decades, X-ray crystallography revealed the atomic structures of thousands of compounds. It showed that diamond consists of carbon atoms arranged in a face-centered cubic lattice. Each atom bonded to 4 neighbors in a tetrahedral arrangement. Graphite, also pure carbon, has a completely different structure. Flat hexagonal sheets of carbon atoms stacked loosely on top of each other, explaining why diamond is the hardest natural substance while graphite is soft enough to use in pencils. In the 1950s, X-ray crystallography provided the crucial data that allowed James Watson and Francis Crick to determine the double helix structure of DNA. Rosalind Franklin's X-ray diffraction images showed a helical pattern with specific periodicities, revealing the geometric arrangement of the molecule's atoms. But in 1982, Israeli materials scientist Dan Shechtman observed something that shouldn't exist. He prepared an alloy of aluminum and manganese and cooled it rapidly, then examined its diffraction pattern. The pattern showed sharp, distinct spots, indicating a regular structure. But the spots had 10-fold rotational symmetry. This was impossible for a periodic crystal. 10-fold symmetry was forbidden by the crystallographic restriction. Shechtman checked and rechecked his results. The pattern was clear and reproducible. He had discovered a quasicrystal, a structure that is ordered but not periodic. Quasicrystals have long-range order, meaning the pattern does not repeat exactly but contains a specific arrangement that extends throughout the material. They can have 5-fold, 8-fold, 10-fold, or 12-fold symmetry, rotational symmetries that are impossible in periodic crystals. The mathematics of quasicrystals connects to Penrose tilings, patterns discovered by British mathematician Roger Penrose in the 1970s. Penrose showed that certain sets of 2 or more tile shapes can fill a plane in a non-periodic way, creating patterns that never repeat exactly but have definite long-range order and forbidden rotational symmetries. The Penrose tiling with 5-fold symmetry uses 2 shapes, a fat rhombus and a skinny rhombus. These tiles, placed according to specific matching rules, cover the plane completely without gaps or overlaps, but the pattern never repeats. Every finite region appears infinitely many times throughout the tiling, but the global pattern is not periodic. Quasicrystals are 3-dimensional analogs of Penrose tilings. Their atoms arrange in ordered patterns that are not periodic, exhibiting forbidden symmetries and creating diffraction patterns with sharp spots but non-crystallographic symmetries. Shechtman's discovery was initially met with skepticism and even ridicule. Linus Pauling, the renowned chemist, insisted that quasicrystals did not exist, that the observations must be explained by twinned crystals or other periodic structures. But as more examples were found and the theoretical understanding deepened, the reality of quasicrystals became undeniable. Shechtman was awarded the Nobel Prize in Chemistry in 2011. The geometry of crystals and quasicrystals reveals deep connections between symmetry, periodicity, and the structure of matter. The regular arrangement of atoms in space determines the properties of materials, their hardness, conductivity, optical properties, and behavior under stress. The seemingly abstract study of geometric patterns and symmetries has direct physical manifestations, governing how atoms come together to form the solid structures that constitute the material world. A sphere has positive curvature. At every point, it curves away from the tangent plane in the same way in all directions. A saddle has negative curvature, curving up in one direction and down in perpendicular directions. A plane has zero curvature, flat in all directions. These local properties, the curvature at each point, determine global properties, the overall topology and geometry of the surface. A sphere is finite but unbounded. Traveling in any direction, you eventually return to your starting point without ever reaching an edge. A plane is infinite and unbounded, extending forever in all directions without closing back on itself. But what about space itself, the three-dimensional space we inhabit? Does it have curvature? Is it finite or infinite? These questions, once purely philosophical, became scientific with Einstein's general relativity. In general relativity, space-time is not a fixed background but a dynamic entity shaped by matter and energy. The Einstein field equations describe how mass-energy curves space-time and how this curvature affects the motion of matter and energy. The geometry of space-time is not predetermined but emerges from the distribution of everything within it. For the universe as a whole, the Einstein equations lead to cosmological models, solutions describing the large-scale geometry and evolution of space and time. Alexander Friedman, working in Russia in 1922, found the first such solutions, describing universes that are homogeneous and isotropic, meaning they look the same in all directions and at all locations on large scales. The Friedman equations show that such universes cannot be static. They must be either expanding or contracting, growing or shrinking over time. This was a shocking prediction, contradicting the prevailing belief that the universe was eternal and unchanging. In 1929, American astronomer Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they are receding. This Hubble expansion provided direct evidence that the universe is expanding, growing larger with time. Tracing this expansion backward, the universe must have been smaller in the past, eventually reaching a state of infinite density, a singularity where the known laws of physics break down. This is the Big Bang, the origin of the observable universe approximately 13.8 billion years ago. The geometry of space depends on the universe's total density of matter and energy. Define the critical density as the density needed for space to be flat, to have zero curvature like a Euclidean plane extended to 3 dimensions. If the actual density exceeds the critical density, space has positive curvature, like the surface of a sphere extended to 3 dimensions. Such a universe is finite in volume but has no boundary or edge. If the actual density is less than critical, space has negative curvature, like a saddle extended to 3 dimensions. Such a universe is infinite in volume, extending forever in all directions. Observations of the cosmic microwave background radiation, the remnant glow from the hot early universe, provide precise measurements of large-scale geometry. The temperature variations in this radiation encode information about the curvature of space. These measurements, combined with observations of supernovae and the large-scale distribution of galaxies, indicate that the universe is very close to flat, with total density extremely close to critical. This flatness poses a puzzle. Why should the universe have exactly the density needed for spatial flatness, when any other value seems equally possible? The theory of cosmic inflation, proposed by Alan Guth in 1980, provides an explanation. Inflation posits that the very early universe underwent a brief period of exponential expansion, growing by an enormous factor in a tiny fraction of a second. This rapid expansion stretches any initial curvature, flattening space just as inflating a balloon flattens its surface from the perspective of someone on it. After inflation, the universe continues expanding more slowly, but the initial flattening remains, explaining why we observe space to be so close to flat today. But space might have more complex topology than simple flatness or curvature suggests. Just as a cylinder is locally flat but globally different from a plane, wrapping around on itself, space could be locally flat but globally finite, connected in non-trivial ways. Imagine a universe shaped like a three-dimensional torus, the three-dimensional analog of a donut's surface. Traveling far enough in any direction brings you back to your starting point, yet there are no boundaries or edges. Such a universe is finite but unbounded, like a sphere, but flat rather than curved. Other topologies are possible. Space could be a three-dimensional Klein bottle, a shape that is non-orientable, having no consistent notion of inside and outside. Or it could have other identifications, wrapping around in complex ways that create a finite volume from flat space. Observations have not detected such topological features. If space wraps around, the scale is larger than the observable universe, beyond what we can currently measure. The universe might extend far beyond what we can see, with its global topology remaining unknown. Black holes present another geometric extreme. Near a black hole, space-time curvature becomes extreme. At the event horizon, the boundary surrounding a black hole, time and space exchange roles in a mathematical sense. Inside the event horizon, moving toward the center is not a choice but an inevitable consequence of the structure of spacetime itself, just as moving forward in time is inevitable outside. At the black hole center is a singularity, a point where curvature becomes infinite and general relativity breaks down. The singularity is hidden behind the event horizon, invisible from outside, but its existence poses deep questions about the nature of space and the limits of geometric description. Roger Penrose and Stephen Hawking proved singularity theorems in the 1960s and 1970s, showing that singularities are not artifacts of special assumptions but generic features of general relativity. Under very general conditions, spacetime must contain regions where curvature becomes unbounded, where the classical geometric description fails. This suggests that general relativity is incomplete, that a quantum theory of gravity is needed to describe what happens at singularities. Quantum mechanics and general relativity, the two great theories of 20th century physics, are both extraordinarily successful in their domains but are mathematically incompatible. Unifying them, creating a theory of quantum gravity, remains one of the greatest unsolved problems in physics. String theory and loop quantum gravity, the main approaches to quantum gravity, both propose that spacetime itself has a fundamental structure at the tiniest scales. Space might not be continuously divisible but made of discrete units, a quantum foam at scales around the Planck length, approximately 10 to the power of minus 35 meters. At such scales, the classical geometric picture breaks down entirely. Space and time might not be fundamental but emergent properties, arising from more basic quantum degrees of freedom. The geometry that seems so fundamental, the stage on which physics plays out, might itself be a derived concept, applicable only at scales much larger than the quantum foundations of reality. The shape of space, from the curvature around planets to the topology of the universe as a whole, remains an active area of research where geometry, physics, and observation converge to reveal the structure of reality at the largest and smallest scales accessible to human inquiry. The honeycomb is a marvel of geometric efficiency. Bees construct their hives from hexagonal cells, each cell sharing walls with its neighbors, minimizing the wax needed while maximizing storage space. The hexagon tiles the plane perfectly, filling it without gaps or overlaps, using less perimeter to enclose a given area than squares or triangles would require. This pattern appears throughout nature, not because nature performs geometric calculations, but because natural processes tend toward efficiency, minimizing energy and materials. Basalt columns, formed when lava cools and contracts, fracture into hexagonal pillars. Mud cracks in a drying lake bed form approximately hexagonal patterns. Convection cells in a fluid heated from below naturally arrange into hexagonal arrays. The scales of a pineapple spiral in helical patterns, the numbers of spirals in different directions following Fibonacci sequences. The arrangement minimizes gaps and optimizes packing as the fruit grows. Sunflower florets spiral outward from the center, again in Fibonacci patterns, placing each new floret at the golden angle from the previous one. These patterns are not designed or planned. They emerge from local interactions, from simple rules operating repeatedly. Each bee adds wax where it fits, following chemical signals. Each new floret forms where space is available, pushed outward by growth. The global pattern emerges from countless local actions, creating regularity without central coordination. Phyllotaxis, the arrangement of leaves on a stem, follows mathematical patterns. The angle between successive leaves tends toward the golden angle, approximately 137.5 degrees. This angle is the most irrational number in a specific mathematical sense, meaning it takes the longest to approximate with simple fractions. As a result, leaves space themselves evenly around the stem over many rotations, maximizing their access to sunlight and rain. The chambered nautilus grows by adding new chambers to its shell, each chamber larger than the previous by a constant factor. This generates a logarithmic spiral, a curve that maintains the same shape at all scales, appearing the same no matter how much you zoom in or out. The spiral is not the golden spiral exactly, but approximates it closely. Spiral galaxies exhibit similar forms, arms sweeping outward in logarithmic spirals. These spirals are not rigid structures rotating as a whole. The stars orbit the galactic center at different speeds depending on their distance. The spiral arms are density waves, regions where stars and gas are compressed, triggering star formation. The pattern persists while individual stars move through it, like cars bunching in a traffic jam that travels at a different speed than the cars themselves. The spacing of planets in the solar system once seemed to follow a numerical pattern called the Titius-Bode law. This rule, formulated in the 18th century, gave a sequence that approximated the distances of the known planets from the Sun. When Uranus was discovered in 1781, its distance matched the law's prediction, and when the asteroid belt was discovered, it filled the gap where the law predicted a planet should be. But Neptune's distance violated the law, and we now understand that the Titius-Bode law is not a fundamental principle but a mathematical coincidence. Some resonances and spacing patterns in planetary systems arise from gravitational interactions and the dynamics of planet formation, but they do not follow a simple universal formula. Quantum mechanics introduces geometric patterns at the atomic scale. Electrons in atoms occupy orbitals, regions of space where the probability of finding the electron is high. These orbitals have specific shapes: spherical s orbitals, dumbbell-shaped p orbitals, more complex d orbitals, and f orbitals. The shapes arise from solving the Schrödinger equation, which describes how quantum wave functions evolve. The solutions have nodes, surfaces where the wave function equals zero, and these nodes create the geometric structures of orbitals. The chemistry of atoms, their ability to bond and form molecules, depends on the shapes and orientations of these orbitals. Crystals of carbon illustrate how geometry determines properties. Diamond has each carbon atom bonded to 4 neighbors in a tetrahedral arrangement, creating a rigid three-dimensional network. This structure makes diamond the hardest natural material. Graphite has carbon atoms arranged in flat hexagonal sheets, bonded strongly within each sheet but weakly between sheets. This allows the sheets to slide over each other, making graphite soft and slippery, useful as a lubricant and in pencils. Graphene, a single layer of graphite, is a two-dimensional material just 1 atom thick. Its hexagonal lattice of carbon atoms gives it remarkable properties: extraordinary strength despite its thinness, excellent electrical and thermal conductivity, and transparency. These properties emerge from the geometry of the hexagonal lattice and the quantum mechanics of electrons moving through it. Buckminster fullerene, discovered in 1985, is a molecule consisting of 60 carbon atoms arranged in a pattern identical to a soccer ball. 12 pentagonal faces and 20 hexagonal faces forming a truncated icosahedron, one of the Archimedean solids. This purely geometric form occurs spontaneously when carbon vapor condenses under certain conditions. The molecule is named after architect Buckminster Fuller, who designed geodesic domes using similar geometric principles. Fuller's domes are stable, efficient structures that enclose large volumes with minimal materials, their strength arising from the triangulation of their surfaces. The same geometric principles apply at molecular and architectural scales. Foam follows precise geometric laws. In 1887, physicist Joseph Plateau asked what structure has the least surface area for a given volume while dividing space into equal cells. For over a century, the Kelvin structure, a specific arrangement of tetracadecahedrons, was believed to be optimal. But in 1993, physicists Denis Wier and Robert Phelan found a more efficient structure using 2 different polyhedra in a specific arrangement, reducing surface area by 0.3%. The Wier-Phelan structure was used in the design of the Beijing National Aquatic Center for the 2008 Olympics. The building's facade follows this geometric pattern, creating a structure that is strong, efficient, and visually striking, a human construction inspired by the mathematics of soap bubbles. Cracks in drying paint or mud, lightning bolts branching through the sky, river deltas spreading across coastal plains, all exhibit fractal-like branching patterns. These patterns arise from similar underlying processes. Energy or material flows through a medium, finding paths that minimize resistance while distributing across space. The result is self-similar structures that look similar at multiple scales. The branching of trees, the structure of lungs, the network of blood vessels, all use fractal geometry to maximize surface area and minimize distance from any point to the center. Nature solves optimization problems through geometric patterns, creating forms that are efficient, robust, and aesthetically compelling without any conscious design. The journey through geometry began with a mark in the sand, a boundary drawn after the Nile's flood. It has traveled through millennia, across cultures, through dimensions visible and invisible, exploring shapes, spaces, curves, and infinities. Now, as consciousness fades towards sleep, the journey returns to its origin. The point. Point has no parts, no extension, no size. It is pure location, position without dimension. The ancient Greeks defined it this way, and the definition remains unchanged. Everything in geometry begins with the point. A line is a collection of points. A surface is a collection of lines. A solid is a collection of surfaces. All structure emerges from this fundamental zero-dimensional entity. The Pythagoreans believed that number was the basis of reality, but behind number was the point, the monad, the one from which all multiplicity arises. The point is both everything and nothing, containing the potential for all geometric forms while possessing no form itself. In Cartesian geometry, points are identified by coordinates, numbers that specify position. But the point itself is not its coordinates. The coordinates are labels, descriptions, ways of referencing the point within a chosen framework. The point exists independently of any coordinate system, a fundamental geometric object that transcends its numerical representations. In topology, points are the basic elements of spaces. Continuous functions map points to points, preserving nearness. Open sets are collections of points. The entire elaborate structure of topology, with its theorems about continuity, compactness, and connectedness, rests on the foundation of points and the relationships between them. In the limit of infinite regress, as we zoom into any region of space, focusing on smaller and smaller areas, we approach points. A line segment contains infinitely many points, densely packed. Between any 2 points lie infinitely many others. The line is completed by its points, but the points themselves are not completed by anything more fundamental. They are the bottom level of geometric structure, the ultimate constituents. Yet points cannot be seen, touched, or measured individually. We perceive only collections of points, regions of space with extent. The point is an abstraction, a mathematical idealization. Physical objects are extended, occupying volume. Even fundamental particles in quantum mechanics are not points in a classical sense but probability clouds, wave functions spread out over regions of space. The point represents the limit of localization, the idea of a position defined with absolute precision. In quantum mechanics, the uncertainty principle prevents perfect localization. The more precisely we know a particle's position, the less precisely we know its momentum. Perfect knowledge of position would require infinite uncertainty in momentum, a physically meaningless state. Perhaps the geometric point, like the perfect circle and the perfectly straight line, exists only in the realm of mathematical forms, the Platonic world of ideal objects. Physical space might be discrete at the Planck scale, made of tiny but finite regions rather than true points. Or space might be emergent, not fundamental, arising from quantum information or other more basic concepts. But even if physical space differs from geometric space, the point remains essential to mathematical thought. It represents the idea of location, of being somewhere, the foundation on which all spatial concepts rest. In meditation practices from various traditions, concentration on a single point serves as a focus for awareness. The point of attention might be the breath or a visual mark or a sound or a thought. The point is not the goal but a tool, a way to gather scattered consciousness into unified awareness. The universe began, according to current cosmology, as a singularity, a state of infinite density and temperature. This is the ultimate point, containing within it all the matter and energy that would expand into galaxies, stars, planets, and life. The Big Bang is the geometric inverse of the black hole singularity, a point from which space itself emerged, growing from nothing into the vast cosmos we observe. As the universe expands, galaxies move apart, space itself stretching between them. In the distant future, if expansion continues accelerating, distant galaxies will recede faster than light can travel between them. The observable universe will shrink, each galaxy becoming isolated, alone in an expanding void. Eventually, stars will exhaust their fuel, galaxies will go dark, black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy, a heat death where no energy gradients remain to power any processes. Space will be nearly empty, filled only with a dilute sea of photons and particles, approaching uniformity, approaching a state with no structure, no change, no distinguishable events. This endpoint, like the beginning, approaches a kind of simplicity, a return to uniformity. But between the initial point and the final fade, between the singularity of the Big Bang and the featureless expanse of heat death, structure emerged. Geometry manifested in countless forms. Atoms, crystals, planets, galaxies, life, consciousness, thought. And within conscious minds arose the ability to contemplate geometry itself, to recognize patterns, prove theorems, discover relationships, perceive the mathematical structures underlying physical reality. The universe, through human minds, came to understand its own geometric structure. The point from which all geometry begins is also the point to which awareness returns in sleep, in meditation, in the final letting go. Thought simplifies, complexity dissolves, the elaborate constructions of waking consciousness fade. What remains is simple presence, existence without content, awareness without object. The journey through geometry has shown how complexity arises from simplicity, how infinite structures emerge from finite rules, how the physical world reflects mathematical patterns. But underlying all complexity, all structure, all forms, is the simple fact of existence itself, the being that allows anything to be. The point is simultaneously nothing and everything. It has no size, yet all sizes are measured from it. It has no shape, yet all shapes are constructed from it. It has no qualities, yet it is the foundation of all geometric qualities. In this formless foundation, in this zero-dimensional beginning, lies the potential for all that geometry has revealed. The straight lines and perfect circles of Euclid, the golden spirals of nautilus shells, the elliptical orbits of planets, the non-Euclidean curves of space-time, the infinite hierarchies of fractals, the patterns hidden in crystals, the topology of the universe itself. All of this emerges from and returns to the point. In the stillness of the night, as waking consciousness fades, awareness touches this foundation, this place before form, this geometric origin from which all shapes arise and to which all complexity eventually returns. The point remains eternal and unchanging, containing within its formlessness the seeds of every possible form, the beginning and end of all geometric journeys, the silent center around which the universe of shapes and spaces revolves. In this return to simplicity, in this recognition of the fundamental, consciousness finds rest. the elaborate constructions of geometry, the millennia of human thought, the vast cosmos of forms and patterns, all dissolve back into pure potential, pure possibility, the infinite creativity contained within the infinitesimal point. And in the darkness of sleep, there is only this presence without extent, existence without dimension. The point that is no point, the awareness that requires no object, the stillness from which all motion emerges and to which all motion returns. The story of geometry is complete. It began with a mark in sand and ends with the erasure of all marks, the return to the smooth surface, the unbroken field, the void that is pregnant with all possibilities. Rest now in this geometric peace, this mathematical stillness, this place where points do not move and forms do not change, where everything is as it has always been and will always be. Simply here, simply present, simply existing in the eternal now that needs no time, the infinite space that requires no extension, the perfect unity that contains all multiplicity within itself. The point, the origin, the end, the eternal return to the beginning, where all journeys start and all journeys finish, in the geometric heart of existence itself. From ancient Egypt to modern cosmology, from the practical to the transcendent, geometry has revealed the patterns woven into the fabric of reality. And now, as sleep approaches, these patterns fade into the singular point of pure awareness, the place of deepest rest. If you enjoyed this journey through the history of geometry, told chronologically from ancient Egypt to the edges of modern cosmology, please subscribe to our channel for more sleep stories that blend education with relaxation. Each story is carefully researched and designed to guide you gently into peaceful sleep while feeding your curiosity about the world. New stories are added regularly, exploring mathematics, science, history, and the wonders of human knowledge. Subscribe now, and let us accompany you on your nightly journey into rest and dreams. Sleep well, and let the geometry of dreams unfold in the dimensionless space of peaceful slumber.